So representing these numbers, again IEEE 754 also include another set of numbers which are called double precision numbers. When you write a C++ program, there are two kind of floats. One is called float, another is called double. So the double means it consumes 64 bits and it's actually a double precision number. And whenever you write float, that represents 32-bit number which is equivalent to a single precision floating point number. Now, in case of a double precision floating point number, the number of bits we got is 64. So again, out of the 64 bits, 1 bit has to be assigned to sign, and then IEEE standard says that 11 bits will reserve for the exponent. So that means, and here we say 1023 is the bias and 0 and 1024 are reserved. So the meaning of reserve bits are same as we have discussed in single precision floating point number. 1024 would represent infinity and not a number, and 0 would mean either 0 or d-normal numbers. Okay, so and rest of the bits, 52 bits for Mentisa. Now because of that, what do we see? We see the precision has increased from 7 digits to 15 digits. So this gives us sufficient precision for most of the mathematical operations. Okay, so similar to this requirement, so you can keep this as an exercise for you, that after this lecture you try to find out yourself that what is the largest double precision floating point number that you can represent and what is the smallest double precision floating point number that you can represent. Okay, so I'll tell you it would be more than 10 to the power 100. So 10 to the power 100 is a very large number. It is the number which you can represent using floating point. This double precision floating point number is more than the whole weight of the universe, the largest number we can think of. Okay, so sometime we also require to represent to be efficient in computation as well as efficient in space. Space means how many bits are required to represent some number. So that's why sometimes we also do half precision floating point numbers. So half precision floating point numbers would be represented in 16 bits. In 16 bits, 1 bit would be given as a sign and 5 bits would be given to exponent and a bias of 15 and 10 bits for Mentisa. So rest of the rules are same as what we have discussed for single precision floating point numbers. Everything else, every rule is same. So for example, here also 31 and 0 exponent are reserved for representing infinity, representing 0 respectively. Okay, so what if I would like to have even more precision than double precision floating point numbers? Okay, so in that cases, for initial some time, like in the past history, so there was initially like different vendors, they were trying to invent their own standardization. So for example, somebody was designing a calculator. Because the part of calculators are not going to be used somewhere else, so they were defining their own precision. So let's say your calculator was showing only 10 digits of a decimal numbers. So the precision can be decided accordingly. So similarly, let's say you're designing a computer which require arbitrarily very large precision, so you could use more number of bits for precision and exponent. So one of the example is Intel's 80-bit format. It's not standardized, but because Intel is leading the industry for last 40 years, so whenever you write in C long double, it will automatically take this 80-bit format. in this 80-bit format, you have more exponent bits, you have 15 exponent bits, your mantissa bits is also 64. So that means precision has increased, the number of the range of numbers which you can express is also increased. So based on our requirement, we can choose these formats. Then slowly IEEE has given more standardization, or like some people have started using more number of bits. So for example, there are 128-bit representation of floating point number, or 256 bits of floating point representation. So all of these floating point representations could be custom made for the custom requirement. We see that if we need to represent more or a larger number or a higher precise number, so we can increase the number of mantissa bits or exponent bits accordingly. So they would be required for very specific applications. These applications could be space, it could be nuclear, it could be any scientific application. Okay, so the idea here is that it gives us freedom to choose how many bits, and because your hardware is going to be custom, nobody else is going to use your hardware firmware, so that's why we can these people can decide their own floating point notations. But if your hardware and software need to talk to each other, let's say we are writing a piece of software which we need to use in Intel machine as well as AMD machine or in some other machines, then the format has to be interreplaceable, or basically all of them should understand the same format. So with this we are almost close. Let's take one example so that we can understand that if some arbitrary precision is given, or some particular precision is given, some format is given, can I convert that number to floating point number? So let's take it with a quick example. So let's say we have taken this example in single precision numbers also. Let's do it with half precision. So we can do it quickly because we have anyway done this in our previous lecture. So let's say the decimal number is 2.625. Now I can represent that number using 2 plus 0.5 plus 0.125. Now we can say the binary number is minus 2 means 10. So binary number is 10, and this is 1, this is 01. So the normal scientific form would be minus 1.0101 into 2 to the power 1. So if I want to represent it in a half precision method, so that means the mantissa would be 10 bits. 10 bits means 4 plus 4 plus 2. So I have divided it like 2 here, and then 4 and then 4. So basically I have started from the reverse so that we can complete the number of bits. And exponent is 5 bits and the base offset was 15. So exponent here was 1. So 1 plus 15 means 16 would be there, and then 16 need to be converted into binary, which is a 5-bit number, that is 10000. Then we can combine all the sign, mantissa and exponent bits and then convert our floating point number. So that means 1 here and then 10000, and then the mantissa bits 01, 01, 00, and so again I would like to emphasize that whenever we are writing number in this way, if we write in a group of 4, then converting into hex would be easier for us. So this 1100 will become C, 0001 is 1, and 0100 is 4, and these 4 zeros will be 0. So this way we can, if we are given any number, we can understand that how to convert that number into a floating point number of half precision, single precision, double precision, or whatever is the given thing. So with this we are we now understand all the various aspects. So let's also see that when do we use floating point number, which number to be used, whether to use single precision, double precision, or extended double precision, and when not to use. So one thing which has been observed you see that whenever we are representing floating point numbers, let's say if I want to do addition in these floating point numbers, how the addition would have to be done? How do we do addition in our scientific form? So first we have to keep the exponents as same, and then we add the decimal part. Okay, fractional part would be added. So let's say the two numbers will have different exponent. First you will set the exponent as same, and then you will shift one of the number so that the exponent is same, and then you will add the fractional part and the non-fractional part. So if all of those things has to be done in binary, it would require multiple different steps. You have to further, after doing all the computation, then again you have to normalize and then represent it in binary. So all of these steps required so many different, all these addition, subtraction, multiplication, they require so many steps that the amount of hardware that is required, or number of cycles, amount of time which is required, both of them are huge. Huge means it has to be with respect to something. So huge means with respect to integer multiplication or integer addition, integer subtraction. So that is why if my application has to be performance oriented, I want to make my application run as fast as possible, I would like to use as many integer calculations as possible, and I would like to minimize the floating point calculations. Okay, so sometime we even try to reduce the floating point multiplication by doing fixed point multiplications. Though precision will reduce, but computation can be done in a fairly fast method. The other thing which we have to understand with these floating point numbers, that whatever precision we keep, they are not infinite precision. Even in case of double precision floating point number, the amount of digits are 15, and we have a lot of irrational numbers where whatever number of digits you have is less. So for example, pi. So all of these numbers will have so many digits, and you would say, why does it matter? A digit which is less significant than the 10 is power minus 15 or 2 is power minus 1024, why it should be significant? So it becomes significant when it accumulates. At many places we keep on doing computation, and let's say the computation is multiplied with some large number. The error would be, the approximate error would be equal to the multiplication factor. So this accumulation, because of multiplication, because of addition, subtraction, every operation will introduce its own error, and those error will get magnified when we'll have this multiplication operations or division operations. So that's why many a times we prefer to use double precision numbers if that error should be very less. Whenever we want to have this quantization error, this is called quantization error, because we are trimming, we are saying that we cannot represent smaller than this number. So whenever we have these quantization numbers, quantizations thing, then and accumulation is happening, then instead of single precision we go for double precision number, so that the amount of error can be reduced. Okay, so and that's how we choose that which precision we have to choose. So different, if the number is of a higher precision, then it will be using that, we can use that for lesser error. Now sometimes we also do these operations that we convert floating point number to you also sometimes typecast, let's say double precision number to single precision, or single precision to double precision. Let's say you are converting a single precision number to a double precision number. Single precision has only 23 bits, but 23 bits of precision, but double precision has 52 bits. Now these 52 bits, so that means rest of the bits I have to make at 0. Okay, so if reverse is the case, we don't know what rounding technique we have to use. There are various rounding techniques. So based on these rounding techniques, sometime you will keep the MSB as 0, least significant bit as 0, or sometime you will keep least significant bit as 1. So these rounding will also create different results for different scenarios, for different conversions. So all of these things should be reproducible. Reproducible means that every computation should give certain definite results. So hardware will try to make sure that whatever method is being followed for rounding, for precision, for accumulation of error, that should be standardized, so that should be fixed, or so that it could be repeatable. Okay, so with this we close this particular topic of floating point numbers, and essentially we can summarize this whole topic as the numbers, depending on our representation, we can have various formats, and depending on the requirement, we can have different formats as per our requirement. This is also conclusion of our module 1, which means binary representation. So as a summary of this module, what do we summarize? We can say that a binary number, although it is only collections of zeros and ones, but the same collection of zeros and ones can be used to represent a signed number or an unsigned number. And in unsigned number, in a signed number, there could be various possibilities. I can represent it using 2's complement, 1's complement, or offset method, or sign magnitude method. So all these combinations are there, and the same zeros and ones can be used to represent some symbols, some text. Okay, and same zeros and ones can also be used to represent floating point numbers, as we have discussed in this lecture. So that means it is not only important to know what is 0 and 1, we should also know that this collection of zeros and ones is representing what. So some additional information should be provided. It is mostly context dependent. Based on the context, you know that this number, so for example, whenever you are writing your C++ programs, so you say specifically that this is the type of this number, whether this number is a int, whether this number is a character. And somebody in the hardware is taking care that if you are representing that number as an integer, it should always be considered as integer, unless you typecast it. When you typecast it, then you are asking hardware to not consider this number as an integer, but let's say consider it as a float or character or the array of characters. Okay, so the interesting thing is these zeros and ones are not only representing data in various forms, but it also represent applications, instructions, commands, or signals. So based on these signals, various operations can be performed, and that's what we see during this whole course, that that zeros and ones is a powerful mechanism to do various operations, to represent data as well as to represent different control signals, different commands, or different instructions. This is at one level of abstraction. At higher level of abstraction, you can also see that these zeros and ones can be used to represent applications. So if you say Microsoft Word, what is it? It's an application written in a binary form, 0-1 form. So if you see Microsoft Word document, that Word document is also a collection of zeros and ones. And in the Microsoft PowerPoint, let's say, in the PowerPoint I am writing this whole array of characters and some symbols. So all of those things are further encapsulated and written within Microsoft PowerPoint. And all of you know that all these data, so all these applications, which means you can say documents, movies, presentations, songs. All of these are binary representation, and the application which are understanding, which are running them, are also binary representation. Your MP3 movie player or MP3 player or a movie player, M player, all of these are also some binary application, to the extent that your operating system is also a binary representation which loads all the computer and works on it. So in summary, these zeros and ones can be used to represent anything, and many other times you would try to define your own custom understanding, custom representation of these zeros and ones. And because we are working at the lowest level of abstraction in this course, so we will see that these zeros and ones are represented either using integers, signed, unsigned, text, ASCII characters, floats, or command, signals, instructions. With this, I would like to close. Thank you very much. We'll start with a new module in the next class. Thank you very much.